All right, so this is our last few sections here. We've got 7.1 and 7.2. And in these sections, we're going to talk about functions of several variables. So in this first example here, I have c of x comma y equals 700 plus 70x plus 100y. Up until this point, we've really only looked at functions of the form, y equals f of x equals 2x squared minus x plus whatever the function looks like, right? Our function only has this one variable. Now we're going to start to talk about functions of two variables or three variables or four variables. We have multiple variables. And what's cool about these is if you think about the types of functions that we've looked at so far, this y equals f of x. When you graph this on an xy coordinate plane. You live on a flat piece of paper. And regardless of what it looks like, here we have a parabola. Perhaps it looks something like this. It's a two-dimensional shape here. When we start to look at these functions of several variables, so here I have a function of two variables. Another way I could write this is z equals 700 plus 70x plus 100y. Another way I could think about this, if I was to graph this is no longer a two-dimensional shape because I have x, I have y, and now I have this third variable z. So I don't live in two dimensions or two space anymore. I actually live in three dimensions, in three space, which is where you and I live. So if you were to graph this, what you would actually see, rather than living on an xy coordinate plane, you would live in the x, y, z coordinate space. So here you would have x, y, and z right here, and you would actually have three-dimensional shapes. So imagine this is kind of like the corner of a wall or the corner of a room. And that's what it would look like. You would live in three-dimensional space, and we can do all sorts of really neat stuff with these. We can graph these three-dimensional shapes, and then we can start to ask really cool calculus questions like, okay, what does a local minimum look like in three space? Because you can actually have things which are local minimums if you look at them from one perspective, but actually local maxima from another perspective. It's very cool. But we're going to just focus right now on the very, very basics of this here. So we're just going to start by just getting used to these functions of several variables here. So here I have this cost function, like I said, c of xy equals 700 plus 70x plus 100y. I want to find c of 20 comma 10. So really in this first section, we're just going to get used to working with functions with several variables, just kind of evaluating them. So if I wanted to look at c of 20 comma 10, I'm going to take 20, I'm going to plug that in for x, I'm going to take 10, plug that in for y, and then evaluate the expression that I come up with. So 700 plus 70 times x, we said x was 20, plus 100 times y, that's 100 times 10. Here I've got 700 plus, what do I have here? 1400 plus, this will be 1,000, so I've got 21, I should have 3,100 here. There is my result. So really I just want to get used to seeing functions of several variables, working with them, evaluating them. This first section is going to go really, really quick. So we can also write familiar geometric formulas as functions of two variables. So if you look at, say, the volume of a cylinder is pi r squared h, where here my volume depends on both r and h. So when I say find v of 5 comma 4, I'm really looking for the volume of a cylinder who has a radius of 5 and a height of 4. But I'm just going to take these two and plug these in. So v of 5 comma 4 equals pi times r. R, we said that's 5, so 5 squared times h is 4. So here I have pi times 25 times 4, which would be 100 pi. And you could, of course, go get a decimal approximation if you wanted to, but I'm going to leave my answer in terms of pi. And there's nothing to say that we have to stop at functions of 2 variables, right? So I can also work with functions of 3 variables, f of x, comma y, comma z. Now, if you start to ask the question, what does that look like graphically? That's a much harder question to answer because now you're living in 4 space, you're living in 4 dimensions. And if you're curious about this, look up the shape. In 2 dimensions, we have a shape with 4 equal sides. It's called a square. So this is in 2 space. In 3 space, if we kind of expand that out, we no longer have a square, we have a cube. So this is 3 space. If you were to look in 4 space, you no longer have a cube. Instead, you have what's called a hypercube, which there's really not a great way to visualize it. This is what we use to represent a hypercube, and I'll actually write that down, hypercube. And it's just a super cool shape. If you just Google hypercube and go to the Wikipedia page, just look at a rotation of it, and it looks like it's moving. It's so freaking cool. I think it's awesome. You don't need to know that. I just think it's kind of really cool. But here, we're just going to work with this function f of x, comma y, comma z. We're going to evaluate this at f of -2, comma 2, comma 3. So let's see, f of -2, comma 2, comma 3. So let's see, I have 2 times x, that's -2 squared, minus 3 times x is -2, times y is +2, plus 3 times z, well, that's 3, plus 1. And then we're just going to evaluate this expression. So here I have 2 times 4. Let's see, this will be plus 6 times 2, plus 9 plus 1. This is 8, plus 12, plus over here I'll have 10. This should be 20 plus 10. I should end up with 30. So there's nothing to stop you from saying, okay, what if I had a function of 20 variables, right? Or 26 variables. You use every letter of the alphabet. You could use more than that. You could have a function of 100 variables. And actually, we see weird stuff like that. The higher you go into math, the weirder stuff you see. And you start to see functions of several variables. So I think it's kind of cool, but you may disagree. But for now, we're going to stick to functions of 2 or 3 variables. The last example here for this section, like I said, this is a really short section. Here I want to find g of y, which I'm going to call g of 0, comma y is equal to the function, or excuse me, for the function, and here I have a typo, g of x, comma y is equal to 2x squared minus 7xy plus 3y squared minus 10. So when we look at g of 0, comma y, hopefully we can kind of guess what we're going to be doing. I'm going to take 0, I'm going to plug that in for my x value, and y I'm actually going to leave alone. I'm not going to change that y value in any way. So I'm going to say 2 times 0 squared minus 7 times x is 0 times y, I'm just going to leave that as y, plus 3y squared minus 10. So in this case, 2 times 0 squared, this would be 0. Negative 7 times 0 times y, that's going to be 0. I should just be left with 3y squared minus 10. We can also do other kind of unique things with these functions of 2 variables. So I might say, hey, I want to find g of y, comma y. And this means, hey, take y, plug that in for your x value. So let's actually see what that would look like, just because I think it's a neat question. Here, let's see, 2 times y squared minus 7 times x, which I'm going to plug in y, times y, plus 3y squared minus 10. So I have 2y squared minus 7y squared plus 3y squared minus 10. The only thing I have left to do is combine my like terms. So let's see, 2 minus 7 would be negative 5, plus 3 I'd have negative 2y squared minus 10. So you can do some neat stuff with functions of several variables, things that we're perhaps not used to seeing, but hopefully it shouldn't be too earth-shattering or mind-blowing. In this section, 7.1, we're really just making sure we kind of see functions of several variables and can evaluate them at different coordinates. But of course, this is calculus, and I want to be able to do cool calculus stuff with these. So I want to be able to say, okay, well, let's talk about derivatives. And here's where we actually come back and talk about derivatives for one last time. We have what's called first-order partial derivatives and second-order partial derivatives. So here we have first-order partial derivatives. And actually here I have a little bit of a typo. I don't think I had the right variable available for me. Most of the time we'll see first-order partial derivatives written like this. So here we'll have, say, f of x comma y be some function of both x, y. So it would be, 2x squared minus 3xy plus y minus 1. Perhaps it looks something like that. But what's important that it's a function of both x and y. Most of the time we'll see this notation right here, f sub x of xy. And this represents the partial derivative with respect to x. The other way that I could write that, you may see this in the homework, you may see this notation, rather than we're used to seeing dx over dy, or perhaps we might see dy over dx, excuse me, that's kind of what we're more used to seeing. So we might see in this case df over dx. Since we have these two variables already, we're used to saying like z is equal to a function of x, y. And what we want to do for partial derivatives here is we're not going to use the letter d, instead we're going to use the Greek letter del, so del z, del x. So this says the derivative of z, or excuse me, the partial derivative of z with respect to x. So you may see this notation pop up in the homework. I'm going to stick to this notation as much as possible, but just so you're aware, you may see this pop up from time to time. And then similarly for the partial derivative with respect to y, again, we're going to see f sub y of x comma y more often, but you may also see this as del z del y of f sub y of x comma y. So let's talk about partial derivatives, because these are a little bit tricky. But once you get the hang of them, I think they're actually, they should be mostly review. It's just kind of an initial learning curve that we're going to have. So here, z equals f of x. Oops, again, I have a mistake here. This is f of x comma y is equal to 2x squared minus 3x squared y cubed plus 5y plus 1. So here I want the first order partial derivative with respect to x. So what that means is I want to, and I'm going to write this over here, find the derivative with respect to x. And another thing that this means, and this is, I think, the trickier part right here, we're going to treat y as a constant. So let's just rewrite our function right here. So f of x comma y, this is equal to 2x squared minus 3x squared y cubed plus 5y plus 1. So I want to keep this stuff right here in mind. We're finding the derivative with respect to x, and we're treating y as a constant. So it's going to follow all of the same derivative rules that constants do. So when I go to take the derivative f sub x comma y, if you have a term that only has an x, so first I have 2x squared, you're going to take the derivative of that exactly like we normally would. So the derivative of 2x squared, that is simply 4x. Then you might run into some terms that have both x and y. And what I'm going to do here, so I'm going to say for the purposes of this problem, notice we're taking the partial with respect to x. I'm going to cover up y for a second. Just pretend it's not even there. Just pretend that's not even there. Cover it up on your paper. Say, okay, I want the derivative of negative 3x squared. Well, the derivative of negative 3x squared, that's going to be negative 6x. But that y is still there. If you look at the derivative rules for constant multiples, it means we just multiply the derivative by that constant. So we're going to multiply our derivative, which is 6x, by this constant, which is y cubed. So really I have the derivative, which is right here, 6x times y cubed. This is just a constant multiple coming down into the first derivative with respect to x. Then I see this right here, a term that only has a y. So here's where this is going to come into play a little bit more. Hopefully this will be a little bit more easy to digest here. It says treat y as a constant. So that means 5, which is a constant, times y, which is a constant. This term right here, 5y, that is a constant. Well, I know that the derivative of any constant is 0. And 1, well, that's a constant. We're used to seeing that derivative of that is 0. You don't necessarily need to write in 0, but I like to do that here just so that it's very clear exactly what's going on. So my first order partial derivative, f sub x, of x comma y, is 4x minus 6xy cubed. Here is my first order partial derivative with respect to x. And then, of course, I can evaluate my first order partial derivative at a certain point. So here I would like to evaluate my first order partial derivative at 2 comma 3. So here f sub x of 2 comma 3. Hopefully we understand exactly what this means, but if not, we're just going to take 2, plug that in for x, 3, plug that in for y, and evaluate it. So here I have 4 times 2 minus 6 times 2 times 3 to the third. So this should be 8 minus, here 6 times 2, I should have 12, 3 to the third, that's 27. So let's see, 8 minus 12 times 27. I don't trust my arithmetic here on this one, 324. So let's see, I should have negative 316. All right. Now, I want to say, okay, well, here's the partial with respect to x. That's all well and good. Now, I would like to find the partial derivative with respect to y instead. So I'm going to go back to that original function. I'm going to go back to f of xy, which is 2x squared minus 3x squared y cubed plus 5y plus 1. So here in this case, we can kind of follow these same directions that we were looking at. We're just going to kind of switch around x and y. So we want derivative with respect to y. And this time we're going to treat x as a constant. So when I go to find the first order partial derivative with respect to y, so I want f sub y here, I'm going to look at this term right here, 2x squared. 2, that is a constant. X, which is a constant, being squared, that is a constant. I have a constant times a constant. So this whole term is a constant. Derivative of a constant is 0. So I'm just going to put that 0 there so I know exactly what's happening to that term. Derivative of that term is 0. Next, I move over here to negative 3x squared y cubed. Here I have this term that has both an x and a y term. So again, just like I did with the in the last example, I'm going to cover up my opposite variable. So I'm going to cover up this x here for a second. Pretend it's not there. So I really want to say, okay, well, I want the derivative of negative 3y to the third power. And I'm going to take the derivative of that like I normally would here. Well, that would be negative 9y squared. But the constant, because we're multiplying by that constant, the derivative of that part isn't 0. We just multiply the derivative by that constant. So we're going to multiply the derivative by the constant, which in this case is x squared. So this x squared is just coming down into the next step. Same thing happened over here with this y cubed. Notice this y cubed just came down into the next step. All right, so we have our first few terms, plus next up I've got a term that only has a y. This should be a little bit more manageable. Derivative of 5y, that's just plus 5. And then the derivative of 1, well, that's just 0 since it's a constant. So my first order partial derivative with respect to y is negative 9x squared y squared plus 5. Here is the first order partial derivative with respect to y. Notice that the first order partial derivative with respect is different, the first order partial derivative with respect to x is different than the first order partial derivative with respect to y. So you will not get the same thing if you take the partial derivative with respect to x and the partial derivative with respect to y. We should have two separate derivatives. And then, of course, I may want to evaluate that at a certain point. So, okay, we're going to go ahead and take our partial with respect to y. And actually, let's change our color up here. Let's do this in black. So I want to take 4, plug that in for x, 1, plug that in for y. So here I have negative 9 times 4 squared times y is 1 squared plus 5. So I have negative 9 times 16 plus 5 here. So 9 times 16, that gives me minus 144 plus 5. Here I'd have negative 139. So I think this is the tricky part right here. It is to treat that opposite variable as a constant, treating that variable that you're not thinking about here. So if I'm taking the partial with respect to y, treating x as a constant. This is probably the most difficult part of this section, but once you have it down, we're using all of the same derivative rules that we've been using. So we're still going to be using the power rule most of the time. We may still need, on occasion, the other derivative rules. So in the next video, we're actually going to see what does it look like if we need a chain rule. Then we're also going to say, okay, what happens if we want, say, a second derivative? What does that look like? So take a look at our next video, which is, unfortunately, it's our last video.